Bum ba da bum. Welcome back, Earth Science. Today we're going to talk about Chapter 9, which is all about volcanoes. These very explosive, cool parts of the Earth's, Earth spheres and geology sphere. These very cool, explosive at times structures. Let's jump right in. Let's get started on some volcanoes. So first off, we need to define a definition for what is a volcano. And a volcano is an opening in the Earth's crust through which molten rock, gas, or ash erupts. And we get these when magma rises to the surface. So magma is that really hot rock that's usually in the mantle and the crust, the mantle and the cores. When it makes it up, it becomes these very hot magma. Now the asthenosphere, the very top layer of the mantle, is solid. So some of this material has to melt to form actual magma, to form this actual liquid kind of rock component that gets able to be ejected through a volcano. So magma formation, there's three conditions that kind of lead towards magma formation. The first is a decrease in pressure. This decrease in pressure underneath the surface creates a lowering of the melting temperature of the asthenosphere. This is very common in rift valleys in mid-ocean plates. Remember, as we have these slab pull and ridge push, and all of these plates are being moved to the sides here. This asthenosphere now has more room to come up here, less pressure, and it can melt and form this nice lava, which will come through this volcanic vent over here. The other two factors are an increase in temperature. So the asthenosphere is hotter in that area. For some reason, that plume of the mantle is hotter. This can create things like hot spots. This hot magma is able to get through the crust, able to melt more. And the third thing is an increase of water in the asthenosphere. And this can lower the melting temps. And this is really common when we have those oceanic plates getting subducted underneath of another plate. If I have two oceanic plates here, this one that's getting subducted underneath is going to take some of that water with it. And now all of a sudden we have this asthenosphere that can melt and these volcanoes that can form on the surface. So which boundaries are volcanoes common at? Both divergent, where these two plates are moving away from each other, and subduction, where they're coming together, divergent, and then one's diving down beneath, are ideal for magma formation. So we see most of our volcanoes at these boundaries. Once this magma forms, it rises to the surface because it is less dense than the surrounding rocks. It's hotter, it's less dense. Hot, less dense things are going to rise. They're going to move upward. So at subduction boundaries, we get these volcanoes as this oceanic plate gets pushed underneath the continental, or an ocean is moving underneath another ocean. When we have this, the volcano will always form on the top plate. So if I have this oceanic plate going underneath the continental, this volcano will form here on this one that's above or on the top here. And I'll have some little magma flowing down here. Some little smoke clouds. But volcanoes will always form on this top plate. So when we see volcano chains or volcanic island chains in the ocean, they are forming on this top plate here. So when this oceanic plate goes underneath another one, a continent or another ocean plate in the form of a continent, it's going to form volcanoes inland on the continent. This is how we got the Cascade Range. For ocean to ocean subductions, this creates a chain of volcanic islands. This is a chain, it's called a volcanic island arc. The Marianas Islands in the Pacific are an example of one of these volcanic island arcs. At divergent boundaries, where we're below a rift and these plates are splitting apart, the pressure in the mantle is lower, causing this lower melting temperature. High temperature and low pressure cause a large amount of magma, and this magma is less dense, so it will rise up towards the surface. As it starts to cool, we have that slab pull moving it down, that ridge push moving it down, that gravity sliding. So we have more room for more magma to come up. Most of the magma actually that reaches Earth's surface comes from these divergent boundaries. And most of the rifts in the world are underwater. So most of Earth's volcanic activity occurs underwater. Iceland is a kind of unique example, as it actually has a mid-ocean ridge which is at sea level, or above sea level, excuse me, and much of Iceland has volcanic and geothermal activity because of this. We also get volcanoes over hotspots. These are areas of volcanic activity that result from plumes of hot solid material that are rising from deep within the mantle. The hotspot doesn't move, but the plate over it does. So if I have an oceanic plate that's moving this way, at one point in time, it's going to form this volcano here. And as this plate moves, in this second example here, this island will now be over here, and a new one will be under this spot. This hot spot doesn't move. This plate is just moving and carrying these islands along with it. This formation and this process is how the United States got Hawaii. Well, and colonization, but this is how Hawaii was formed. The Lohi Seamount is a very young, very active volcano off the coast of Hawaii. In tens of thousands of years, it will become our next Hawaiian island. You can see that these Hawaiian islands are moving this way. This chain is moving this way over this hot spot. So this one should form here. So magma and erupted materials. Not all magma is the same. There's different types of magma. And this different type of magma is determined on how much silica is in it. Remember, silica was silicon and oxygen. So this principal ingredient for magma determines its viscosity or resistance to flow. Water isn't a very viscous liquid. Things like molasses, which flows a lot slower, is very viscous, meaning it has a resistance to flow. And the same way, magmas that have high silica are going to resist flow. They're going to have a higher viscosity. Low silica magmas are going to flow fast. They are going to have a low viscosity or lower viscosity. Now, not just molten rock is inside of magma. Sometimes you can get these gases that form inside of magma. They are made of mostly water vapor and carbon dioxide. As magma rises, these gases can bubble out into the surrounding air, into pockets. In viscous gases, this gas cannot escape because it is very, very thick. And when it finally does expand and propel the magma to the surface, it is very explosive in nature. So high viscosity magmas are more explosive. Low viscosity magmas are less explosive. So types of magma based on location. The most common place we find basaltic magma is at rifts and at oceanic hotspots. It runs better, it runs faster. So it's going to create this nice smooth coating on the ocean floor. Andesitic magma, this is found at subduction boundaries. And then rhyolitic magma is found from hotspots that are formed underneath continental plates. So as you can see, we're kind of moving from less viscous here, a little bit more viscous, moving onward and onward. All right, lava flows. Lava usually has a very different composition than magma. Lava is magma at the surface. Lava is going to flow on land. And these basalt flows from this lava are usually going to be less explosive. The temperature and the speed of the lava are going to affect the appearance of the basalt's hardened surface. And we have two names for solidified lava flows. The first is Pahoho. This is lava with this smooth, almost rope-like surface. It's very, very high temperature. It comes from the Hawaiian words to paddle. In A'a, this is this rough, jagged surface lava, moves much slower. It is cooler, and so moving slower, it's more viscous. And it comes from the words to burn. And it kind of covers these jagged, rough structures, where this one is this smooth, rope-like structure. Underwater, we get lava flows, and they form these really cool, distinctive shapes. These are rounded, kind of pillow-like forms. They have a very hard exterior crust. You can kind of see this one that's broken open here. When we get pressure in the inside, these can break open, and then another pillow shape will form in front of it. These resulting round masses are what we call pillow lava because of their very round, kind of like airy kind of shape. They resemble a pillow. Now, not all magma that gets injected is lava. Some of it is ash and rock fragments. When this magma has these trapped gases in it, we get a very explosive eruption. And we call this stuff that gets erupted, these solid fragments, pyroclastic material. Pyro meaning fire, clastic meaning chunks. When we talked about clastic sedimentary rock, it was the stuff that was kind of big chunks. So this pyroclastic material are the solid fragments that are ejected. We classify these by their size. Ash is the smallest pieces, lapilli are our medium-sized pieces, and our largest pieces are called blocks and bombs. Another thing we can get on volcanoes is this pyroclastic flow, where these hot gases are mixing with pyroclastic material to create almost a liquid that is flowing. These form a dense, superheated cloud that is traveling down the volcano at really very high speeds. And Mount Vesuvius is the most famous of these, producing a flow that buried the Roman city of Pompeii under pumice and ash. There was a lot of this pyroclastic material. People were basically breathing in this superheated cloud, pretty much mummified the entire town very quickly. So volcanic landforms, the shape of volcanoes are determined by the nature of how they erupt and the material that they eject. So shield volcanoes, our first one, they have low viscosity lava, which remember has low silica. This lava will flow a long way off the central vent before it hardens. This makes a very broad base on this shield volcano. And this broad base can support really, really tall structures. These are made out of basaltic lava. This is why they're less likely to erupt. These are less explosive volcanoes. These are kind of the ones that just kind of flow out, kind of pool out magma. They harden, it heats up again, pools out magma, and the cycle continues. Cinder cones, these are formed when molten lava is thrown into the air from a vent. As the lava falls back down, it breaks into fragments, it hits the ground. These fragments accumulate and form this kind of cone-shaped mound with an oval base. Composite volcanoes, these develop when layers of materials accumulate around a vent. Mount St. Helens is an example of a composite volcano. On Mount St. Helens, we had what's called lahar. Lahar is hot ash mixing with snow and ice. And it creates this very fast moving mud flow that is very hot that can reach depths of up to 46 meters or 140 feet. Calderas are these large crater-shaped basins. Crater Lake in Oregon is an example of this, as this old kind of top of a volcano filled up with water, became this nice big old lake. Yellowstone Park is an active caldera, where it's got that very large crater-shaped basin underneath. And if it was to, the eruption that caused Yellowstone was 1,000 times stronger than that of Mount St. Helens, why it is much bigger in size. Lava plateaus are formed as a long, narrow crack or fissure in Earth's surface, has this basaltic lava pouring across it and out of it. As it flows across the land, it creates these really kind of flat plateaus. The Columbia Plateau was formed this way as this lava was flowing, creating this very flat surface, as this basaltic lava, which is very low viscosity, so it moves a long way before it cools, kind of smoothed out this whole area. We're going to talk about some extraterrestrial volcanoes. There are volcanoes on the moon. In these dark spots on the moon, this is kind of a map of the moon stretched out. 15% of the moon's area is covered in these dark spots. We thought that these were oceans, early astronomers did, and so we called them maria, which means seas. This is why, like, the craters are the sea of, these maria are like the Sea of Tranquility and other kind of sea names. We now know that these areas are basaltic lava flows. This is very darker lava here that flows out from these vents, flows a long way, forms these nice rounder structures. We think that this was caused by radioactive isotopes inside of the moon's kind of mantle core area as these heated up. As the moon was setting into place, it created these lava flows that created these maria. Mars volcanoes. It has a large number of shield volcanoes that are forming from that basaltic magma, that basaltic lava that is flowing a very long ways. And it is actually home to Olympus Mons, which is the largest volcano in our solar system. There is no other volcano larger than it. The huge size of Olympus Mons led early kind of astronomers and space scientists to think that Mars didn't have moving plates. We now think that they have cooled, but originally we think that Mars did have moving plates. It is so big because Mars is 1/4 the size of Earth, so it has 1/4 the size of gravity around. There are Venus volcanoes. There are 1,600 very large volcanoes on Venus. Most of them are shield volcanoes because Venus's plates are much thicker than Earth's. They aren't moving, they aren't broken as much as Earth's are. Due to its atmosphere and the amount of sulfur we see in it, we think that Venus has many active volcanoes. And the last one is Io that we're going to talk about, and these volcanoes on Jupiter's third largest moon. Io is caught between Jupiter and the 2 large moons of Jupiter, and this extra gravity of being pulled 2 or 3 different ways creates a lot of friction. Enough friction to think that we have volcanic activity on this guy. And we think that these volcanoes on Io resemble early Earth, as we had the large moon. Our moon is much larger than most moons comparatively to their planet, and the sun. As these 2 forces were creating this friction on Earth, we think we had these early volcanoes, which led us to have an early atmosphere. And with the conclusion of Io, this is the conclusion of Chapter 9. I hope you learned something about volcanoes. I hope you enjoyed it. I really enjoy these extraterrestrial volcanoes. It's something that I get very excited about. If you have any questions, let me know, and have a wonderful rest of your day.